My name is Ray LeJoy. I'm from YMC Process Technologies. Bit of a change in direction over the previous presentations. I'm going to talk a little bit more about bioprocessing techniques. So I'm going to talk a little bit about scaling up multi-column processes. Relatively new advances in twin column technology, multi-column technologies has led to fairly significant increases in productivity over the last few years. And so I'm going to talk a little bit about a twin column approach that we've adopted, and give you a couple of case studies very quickly about how that's impacted the industry or our customers. So the first application I'm going to talk about is the capture step of a monoclonal antibody. And then I'm going to switch over, I'm going to talk about a synthetic peptide purification, which is a significantly different type of a process. What's in common between the two processes are the fact that we're going to use a dual column approach. So we're going to use the resin in a very traditional sense. We're not going to change or violate the linear velocities that are typically used, the cleaning regimes or anything like that. We're going to use them very traditionally, but we're going to adjust our process such that we're going to get higher productivity by using a two-column design. Just a very short, brief introduction to us. We are our original companies were Lewa Process Technologies and Chromacon, a Swiss-based company. Were recently combined under YMC Corporation within the last 6 months or so. So that's the beginning of the genesis of our organization. What it's given us is a scalable approach from the benchtop using this small system on the left all the way up through production scale as high as 20 liters per minute manufacturing scale. So if we look at traditional chromatography, the bugaboo has always been about managing or balancing the difference between purity, throughput, and recovery. If purity is your standard, typically, if you want high recoveries, your throughputs suffer, right? If you, in chromatographic terms, overloading the column reduces my resolution inherently. So if I need high recoveries, I can put less on the column so my throughput drops. If I need high throughput, then very oftentimes my recoveries will drop because I'll have to take smaller fractions. So what we're going to try to do is come up with a strategy that allows us to decouple purity and recovery so that we can obtain both. So I'm going to first start talking about antibodies, and that's a little bit of a different animal simply because resolution is so high because of the specificity of the resin. But first we'll start very quickly with the traditional approach to doing antibody capture. First thing we do, and we're talking about protein A resins. The nice thing about protein A is it's extremely specific. Only antibodies are going to absorb to it. So all other contaminants are going to pass through the column. So it's a bit of a different process. But it does a nice job of illustrating how we can increase capacity on a resin. So traditional work, traditionally what we would do is we would inject onto the column, we'd put sample onto the column until we reach this point. This point is considered, if you can see in the bottom right corner, what we call breakthrough. So at this point, we've loaded enough material onto the column that we start to leak antibody off the back end. That's when we would typically stop loading and we would start washing and eluting the material. That piece that's shown in orange is graphically depicting wasted resin capacity. So the difference between static and dynamic binding capacity. So what we want to do is we want to come up with a strategy that we can actually utilize that resin capacity. But in traditional, what we would do is we would get to this point, we would stop feeding, we would wash, and then we would elute the material, we'd clean the column, right? Over time, we'd clean the column, we'd re-equilibrate it, and then we'd put another batch of material onto that column so we would process through the cycle. What we're going to talk about now is a dual column approach, using the chemistries in exactly the same way, but simply looking at a way to increase productivity by increasing unit loading. So what we're going to do now is we're going to start out traditionally with the same exact strategy. And when we reach this point, when we reach breakthrough of the column, what we're going to do is instead of loading onto a single column, we're going to feed onto that column until we reach breakthrough, shown here. And then instead of stopping, we're going to continue loading to get the full utilization of that resin in the first column, and we're going to capture everything that spills over onto the second column. Okay? So now we can capture that. At the end of capacity of that loading step, we're going to wash the free antibody onto the second column, and we're going to decouple the columns, and we're going to elute that first column, lower the pH, increase the salt concentration. So we're going to elute that material in just as we would in a traditional classic batch process. But while we're doing that, we're also going to continue loading onto that second column now. So we're running in two parallel application or processes at the same time. We're going to re-clean that first column after we've eluted it. We're going to re-equilibrate it with loading buffer. And now, as we finish loading or we reach overload on that second column, we're going to recouple the columns. We're going to bring it back, and now we're going to capture the overflow onto the second column. Okay? So, and then what we'll do is after we finish loading that second column, we decouple, we wash, and we simply repeat this cycle until we've completed the operation, we've processed all the material. So what that does for us, it gives us a much higher loading capacity onto the resin. And because resin is primarily dictated, resin life is dictated by the number of cleaning cycles, the more material we can process between cleaning cycles, the more productivity we're going to get out of that resin. So we continue running through the process until we've finished the batch. So what does that really do for us in real numbers? So I've got a couple of applications that we've run here. So if we look on the left-hand side, a small batch, 100-liter batch at 3 grams per liter, fairly typical, kind of on the low end for today's standards. But if we look at the batch data, single column, 20 centimeter column diameter with a 20 centimeter column length. Total resin was used in this application was 6.3 liters of resin, and our binding capacity was 35 grams per liter. Now, one thing I will note that most people, when they're in production scale, aren't running at the hairy edge of how high they can run loading, right? They back off, they have a safety factor. This is their safety factor is set, in this case, by corporate standards, by quality standards. But binding capacity, 35 grams per liter. If we look at they ran 2 cycles to run the process, and they used about 300 liters of buffer to do so. So you can calculate a productivity number based on grams of material purified per liter of resin per hour. In this case, they get about 10 grams per liter per hour. If we now look at the twin column approach, utilizing the same linear velocities for loading and cleaning now, we use 2 columns. We've reduced the column diameter from 20 centimeters down to 10. And we've also reduced the column length from 10 centimeters down, or from 20 down to 10 centimeters. But that's a little misleading because remember, we're using 2 columns. So our total column length when we're in dynamic binding mode, if you will, when we're running together, is still 20 centimeters. But we can decouple those columns for certain unit operations. The end result of the data shows that our loading is about 65 grams per liter. So we've almost doubled the loading per resin. So what that gives us, the advantages it gives us is, first of all, we needed much less resin. So we've gone from a little over 6 liters to about 1.5 liters of resin. Now at $12,000 to $15,000 a liter for this resin, that's a significant savings on small scale, right? We've also used significantly less buffer because, again, we've been able to put more material onto the column, recognizing that those other unit operations are unchanged. Our product produced per liter of buffer used goes up or drops down, so we're using less. So we have higher productivity gains. Our second application is a 2,000 liter fermentation run or bioreactor run at 5 grams per liter. And again, you get similar data results, right? We went from a 60 centimeter column down to 45. We again we tried to standardize on 10 centimeter column lengths. We keep that fairly consistent between applications on scale up. But our total resin volume now you can see from 56 liters down to 28 liters. So about a 20 plus liter resin savings when you're talking about a $14,000, $15,000 per liter resin is fairly significant. The other driver in this is as you scale up the amount of buffers that can be utilized. So if you look at the buffer savings that you can generate using a dual column approach and combine that with buffer dilution, you can see where you can go from a 2,000 liter buffer tank down to a 200 liter tote or even less when you combine processes. So quite a bit of savings both in floor space and in productivity. So essentially what we do is we take a non-GMP benchtop system and we use a GMP compliant process either Delta V or Rockwell type control and use GMP manufacturing standards. So diaphragm valves, sanitary fittings, things of that nature. And again, our process essentially, when you get to 20 liters a minute, you've run pretty much the largest bioreactor. It can be done in a two-shift operation. So it's also important to note that there's a lot of different multi-column schemes that are available. There's a 2-column design, which is our license. There's a 3-column design. There's as many as you can do a 4-column. You can do as many as 8-column designs. I think the one thing that is agreed upon is that anything more than batch gives you significant savings. So our approach, what we've tried to do is focus on an approach not only gives you that higher productivity number, but also is easier to validate. So 2 columns, less complexity, less analytical instrumentation, easier troubleshooting, less valving, quicker validation, more robust operation. So that's been our strategy during the scale up. Now I'm going to switch gears a little bit, and I'm going to talk about a small molecule, a peptide purification. This is run a synthetic peptide, and it's quite a bit of a different process than what we just talked about. So I'm going to show you a quick illustration of how that works. But if we think about, again, decoupling that purity recovery curve, that's our focus here. So if you see in the graph, as you increase the purity requirements for the product you're fractionating, generally speaking, because of peak overlap, your recoveries fall, right? If you can accept a lower purity product, you get a higher recovery because your peaks can be collected with more contaminants on either end of the overlapping peak. So what we're going to try to do is decouple that yield purity curve again. In traditional chromatography, on the left, what you see is kind of a nice, easy graphical representation of peak overlap. And in a traditional purification process, we would pool those early and late fractions that have product in them that don't meet our purity specification, and we would either lose that material, we'd waste it, or we'd reprocess it manually. That's the current process, right? That's what most people do. And this process called MCSGP, just rolls off the tongue, I know. What we're going to do is we're going to automatically recycle product such that we can reprocess the material of interest that doesn't meet purity specification automatically onto a second column while we're running the first. Again, the key takeaway here is we're doing the gradient elution and we're running the column in a very traditional fashion. We're simply changing the strategy by which we reprocess the cuts, the impure cuts. So in MCSGP, now remember, this is totally different than the capture process. We have that waste material, then we have material that has our product of interest in it, the weakly absorbing material. We have our product, which meets our purity specification. We have strongly absorbing material that does not meet specification. It's on the backside of our peak of interest. And then we have pure waste that we would just get rid of in any process. So we're going to inject this onto the column, and we're going to run our column as if we were running a standard batch process. First thing that comes off, the weakly absorbing material, we just throw that away because we don't want it. Now, instead of fractionating and rerunning this manually, we're going to take that weakly absorbing material that has our product of interest at low purity, and we're going to put it onto a second column. Once we've done that, we're going to decouple these columns, and we're going to collect our pure product on our first column in a traditional sense. And while we're doing that, we're also going to feed more raw material onto that second column. And the reason we're going to do that is we want to set up a situation where we've got a constant mass being injected onto each column as we cycle back and forth. So we need a constant mass. So we feed more material onto the column. Now we're going to take our strongly absorbing material that has product in it that doesn't meet the purity spec, and we're going to cycle that onto the second column as well. And we're going to dilute it with a weak solvent at the same time so it doesn't prematurely migrate through the column. We're going to decouple the columns again. We're going to elute our strongly absorbing impurities and throw them out as we would normally. And now we're going to take that second column, we're going to run that same traditional gradient that we ran on the first column, and we're going to run the process all over again. We're going to take the weakly eluting material, we're going to put it onto the second column with dilution, we're going to collect our pure product, we're going to feed raw material back onto that first column, we're going to recycle the strongly absorbing material that didn't meet spec, and that's the cycle, and that's how we're going to run the process. So we're going to continue through this process until we've processed all of the material. And there you are. So now I'm going to, another quick case study. This is a synthetic peptide that was run a couple of years back. The blue graph you see is the chromatogram of the crude product. That would be the process or the prep chromatogram that was run. The red line underneath it is fraction analysis of the product of interest. And what you see, there's a small impurity peak on the front side of the peak of interest, and then there's a fairly large piece on the back side that has contamination that if in traditional chromatography, we'd either lose, we'd sacrifice, or we'd reprocess manually. I'm not going to spend a ton of time on this. You can see there's a fair number of process steps that are included. The key thing when scaling up this process, though, is going to be maintaining column length. We don't want to change the column length from the early work or from the analytical on batch scale as we go to the dual column technique. So all we're going to do is we would adjust the diameter of the column to increase our scale. Key things, I guess, take away on this one in the bottom left-hand corner. You see overlays of 5 cycles of our product peak, and to the right you see the early fractionation of the impure product. The key takeaway here is our ability to reduce the column diameter of the system and to increase productivity. So at 98.7% purity, which was the customer specification, we went from 19% yield on the first pass of chromatography before reprocessing, and we are able to increase the productivity or the recovery to 94%. So a 4-fold increase in productivity, and that translates to lower solvent consumption and higher productivity numbers as measured as we measure productivity in our laboratory. What this also impacts, though, in peptide synthesis is as your recoveries increase, the synthesis step, the synthesis process can be scaled down as well, because if your goal is to create 10 kilograms of end product and you're losing half of your product, you're at a 20 kilogram scale, right, of manufacturing in order to counter the losses during the purification step. If your losses are greatly reduced, the scale of synthesis can be reduced as well and still meet your end goal. So at the end of the day, our process was such that we went from a 60 centimeter column down to a 30 centimeter column, and total media usage, so this is a reverse phase C18 material, went from 70.7 liters on a single column to 2 columns, each packed with 7.1 liters of resin. Again, the value there is, not in addition to the column packing, is now the equipment supporting the process is also smaller. So a volumetric flow rate of 8.5 liters a minute on the previous system, on the batch process, now translates down to a 3.5 liter system. So now the footprint of your facility can shrink again because the equipment is smaller, the tankage is smaller because the volumetric flow rates are lower. So again, the idea of a handshake, you go from a cube where you do your methods development on a small scale system, scale it up to production scale. And so just some of the products that we've done development work on, synthetic peptides, oligonucleotides seem to be the fastest growing market for us. ADCs for the final ADC conjugate, and CBD oils have become extremely popular as companies, as they try to commercialize CBD so they can be sold across the United States. So I guess did I make up time? If there's any questions I can answer for you, I'd be happy to.
Well, Ray, thank you very much. That was a very insightful presentation. As you said, if there are any questions, now is the first time to ask, but we will carry this on to the panel discussion. If there are not, I once again have a question for you, Ray.
Sure.
Something that popped out from your presentation there was the continuous capture chromatography technologies, and something you pointed out helps diminish some of that high cost of the protein A resin. I think you said $14,000 per litre. It's obviously a huge part of the cost of goods. From the other side of the seesaw, has industry, rather than looking at technology like continuous capture chromatography, has it looked at alternatives to protein A, or is protein A really still the gold standard for monoclonal antibody capture?
Yeah, protein A is still the gold standard. I think what people are more interested in looking at now, not so much changing the chemistry because it's such a proven technology, but changing the orientation of the chemistry. So now you see mobilized, functionalized membranes as a strategy with very, very short residence times because they have no diffusional flow limitations. You also see, in terms of a packing stability strategy, to scale up using a reinforced bed, if you will, of membrane. So a matrix approach so that the resin is supported within the cartridge, if you will, which allows for higher stability under higher linear velocities. So enhanced cleaning flow rates, things of that nature.
So it's still protein A, but it's just the way we
Yes.
use it and the way it's been developed.
Mm-hmm. Yes.
Well, thank you once again, Ray. And if there are no further questions, I would like to invite Kieran and Courtney back onto the stage and we can talk about bottlenecks.